If I told you a quantum chip recently solved a benchmark thousands of times faster than the best supercomputer, would that actually matter for your work? Or is that just another headline? Here's the twist. In late 2025, a handful of breakthroughs quietly changed the ground rules. Qubits, the basic units of quantum computers, started living long enough to do real work. Error correction crossed a critical line where adding more qubits made the computation cleaner, not noisier. And quantum hardware expanded into new regions and networks, so more teams can actually touch this stuff. Let that sink in for a second. Longer-lived qubits, error correction that scales, wider access. So what actually happened, and why should you care? Here's the short version. Princeton researchers announced superconducting qubits with coherence times on the order of a millisecond. That's roughly how long a qubit stays in its fragile quantum state before noise knocks it out. It's like keeping a spinning top perfectly upright in a shaky room. At the same time, Google's Willow chip showed something people in the field have chased for years: below-threshold error correction. In plain English, when they added more physical qubits to protect a logical qubit, the error rate went down, not up. That's the tipping point you need for building bigger, reliable machines. And beyond the lab, the footprint got bigger. Pascal and Aramco deployed the first quantum computer in Saudi Arabia, based on neutral atoms trapped by lasers, and expanded cloud access in Europe. Meanwhile, Fermilab highlighted progress in quantum networking using entangled and squeezed light, a step toward secure links and distributed quantum computing. So let's slow that down for a second. The story of 2025 wasn't one flashy demo. It was a connection of three dots: stability, correction, and reach. Here's what actually matters here. First, coherence time. Think of a qubit like a whisper in a noisy cafe. Coherence time is how long you can hear that whisper before the chatter drowns it out. Most quantum algorithms need a whole sequence of operations, like a sentence, not a single word. If the whisper dies halfway, you don't get the meaning. Princeton's move into millisecond territory for superconducting qubits doesn't sound flashy, but it's a huge deal. Milliseconds give you room for deeper circuits and fewer retries. In other words, you can stack more useful steps before the universe interrupts you. Second, error correction. In classical computing, if a bit flips, we often catch it with parity checks or redundancy. In quantum, the fix is trickier because measuring a qubit destroys its state. So researchers bundle many physical qubits into one protected logical qubit. The catch? If your base error rate is too high, adding more qubits makes things worse. That threshold is the cliff edge, and Willow's below-threshold regime means the parachute opened. When they increased the code size, the logical error rate dropped. It's not universal quantum advantage for every workload, but it is proof that scaling can fight noise instead of amplifying it. In other words, we're not at the finish line, but we can see the path. Third, access and networks. Pascal's neutral atom systems use arrays of identical atoms trapped by light. You can reconfigure them on the fly, like moving chairs on a chessboard made of lasers. That's a very different approach than superconducting circuits, which are etched and frozen at near absolute zero. Both have strengths, both are moving, and with Fermilab's work on entangled and squeezed light, we're watching the early pieces of a quantum internet. Squeezed light means you reduce the uncertainty in one property of light to improve precision. Not magic, just very careful physics. The result is cleaner signals and the ability to link quantum systems over distance. So, why should a team lead or product manager care? Because longer coherence and below-threshold error correction unlock deeper circuits, which unlock more ambitious experiments. And broader access means your team doesn't have to wait for a demo slot in one lab. You can schedule time through a cloud portal, run hybrid workflows, and start building intuition. Let's put some texture on this. A pharma group testing quantum-inspired molecule models can now run longer sequences without the results washing out. That means clearer signals for which molecular pathways to simulate next on classical hardware. An energy analytics team can try neutral atom routines for layout or routing problems, not to replace their optimizer today, but to test where a quantum plus classical approach could trim costs later. A security architect can watch quantum networking demos and get pragmatic about post-quantum cryptography, upgrading defenses while quantum comms mature. Here's where people get surprised. These advances aren't just about speed, they're about confidence. Reliability is what turns a novelty into a platform. And yes, there were headline moments. On certain verifiable benchmarks, Google's systems delivered quantum advantage-style performance, orders of magnitude beyond classical. Quantinuum's Helios system pushed accuracy for general-purpose operations. But the headline isn't the headline. The headline is that the field started to behave like an engineering discipline, pushing error rates down, coherence up, and building out the stack. All right, quick primer, without the jargon. Coherence time. How long the quantum state sticks around. Longer equals more meaningful work. Below threshold error correction, you add more helper qubits, and the overall error gets lower. That's the key to scaling. Superconducting versus neutral atoms. Circuits in a freezer versus atoms held by light. One is like custom silicon, the other is like a reconfigurable optical lab. Quantum networking, using entangled and squeezed light to connect quantum devices. Think secure links and shared quantum resources. If that felt dense, here's the digest. Make the qubits live longer, make the errors shrink as you scale, and make the systems reachable over clouds and networks. That's the recipe. Now the reality check. These systems aren't running your whole portfolio. The strongest results are still on carefully chosen benchmarks or specialized tasks. Cryogenics for superconducting chips is complicated. Wiring thousands, eventually millions, of qubits without creating new noise channels is a real engineering mountain. And we still talk about logical qubits, because most qubits you see advertised are physical qubits, the raw ingredients, not the fully error-protected unit. So let's be precise. The 2025 breakthroughs don't deliver general-purpose, fault-tolerant machines yet. They do show that the bottlenecks, coherence, error rates, and access are loosening. That's a shift from if to how far, how fast, and with which approach. Here's a simple way to think about the hardware landscape. Superconducting chips. Fast gates, mature fabrication, deep cryogenics. Princeton and Google pushed lifetime and error control, which supports error-corrected scaling. Neutral atoms, flexible layouts, potentially large atom counts, room temperature operation for the optics, but still complex control. Pascal's deployments show it's maturing into real environments. Networks, not a computer on their own, but the backbone for secure communication and distributed quantum tasks. Fermilab's squeezed light and entanglement work is about lowering noise and extending range. In other words, it's less VHS versus Betamax and more which tool fits which job and how do they interconnect. Let's talk near-term impact. What can teams actually do now? Cloud providers are integrating more quantum backends. That means more consistent APIs and job queues. You can run small experiments, capture error profiles, and feed that data back into your classical models. Hybrid workflows are getting easier. Tooling from major players is smoothing the handoff between classical simulators and real quantum hardware. You won't need a PhD to submit a calibration-aware job. Standards and benchmarks are solidifying. The industry is converging on how to report error rates, circuit depth, and resource counts. That helps you compare apples to apples. So what about security? If you're responsible for sensitive data, the message is calm and practical. Start your post-quantum cryptography plan now. These new quantum wins don't break today's encryption tomorrow, but they do accelerate the need for a roadmap, especially for data you need to protect for a decade or more. A quick word on geopolitics and access. The Saudi deployment shows quantum capacity spreading beyond a few hubs. That's healthy for the ecosystem. More talent, more experimentation, more perspectives. It also means supply chains, export controls, and standards will matter more. If your work spans regions, you'll want to track where workloads can run and how data can move between classical and quantum resources. Here are a few practical takeaways if this space touches your roadmap. Treat 2025 as a signal, not a finish line. Stability and correction are improving. Plan small, sustained experiments instead of one-off demos. Track the right metric. Logical error rates, not just qubit counts. Ask providers how errors scale as they add protection. Start hybrid. Use classical solvers for the heavy lifting and let small quantum circuits probe problem structure. Think scout team, not main army. Begin a post-quantum security plan. Inventory crypto dependencies and timelines. Prioritize data with long shelf life. Upskill a few quantum translators. Not specialists in every physics detail, just people who can read provider roadmaps and connect them to business needs. What should you watch next? Logical qubit counts that persist for longer durations. That's the North Star for fault tolerance. Error correction curves that keep bending down as systems grow. If that trend holds across platforms, we're in a new regime. More neutral atom deployments and superconducting chips with millisecond-plus lifetimes. Convergence from different directions is a healthy sign. Early quantum networking pilots between sites. Even short-distance, low-rate links matter. They're the internet on training wheels. If you hear those signals, you'll know the momentum's real. Before we wrap, a quick analogy to keep in your head. Classical computing didn't start with the iPhone. It started with room-sized machines, punch cards, and error rates that seem absurd today. The leap wasn't one invention. It was thousands of small reliability wins, stacked together. Late 2025 felt like a few of those wins clicked for quantum at the same time. Here's the thing to remember. Coherence buys time. Error correction buys reliability. Networks buy reach. Put those together, and you move from one-off stunts to systems you can build on. If you're exploring this space, here's how to frame it with your team. Where could deeper circuits uncover structure in our problems that classical heuristics miss? What data would we collect from small quantum runs to improve the classical path today? Which partners can offer transparent error metrics and a realistic roadmap? No magic timelines. How does our security posture change if quantum networking becomes an option for sensitive links? Not directives, just lenses to guide smart bets. One last digest, because it's easy to get lost in the details. Late 2025 gave us qubits that last longer, error correction that scales, and infrastructure that spreads. The result isn't a silver bullet, it's a sturdier foundation, and foundations are what let you build. That's the story for now. If you found this useful, a like and subscribe helps us keep making these videos. Thanks for watching.